You're in math class again. Today, it's quadratics. Again. The person next to you is frantically graphing parabolas. The person behind you is asleep. You're doodling. Maybe thinking about the weather outside. Or maybe thinking about the stock market and the economy if you're smarty pants. And while everyone else is busy trying to work out the turning point of a parabola, you start wondering, what if you kept repeating a quadratic, like plugging the answer back in the same equation over and over again? What happens? You grab a calculator, you try it, and what unfolds is chaos. Literally. Back in the 1970s, a biologist named Robert May was studying insect populations and wanted a way to simulate their growth generation by generation. Instead of using continuous models with differential equations, he rewrote the logistic population model as a recurrence relation like so. This is the logistic map. It models the next generation's population based on the current one, with R controlling the growth rate. May used it because it was easy to compute and match how real population grows in steps. But when he started adjusting R, he discovered something shocking. The system could shift from stable to wildly unpredictable, almost like chaos. Let's play around with values of R. When R is within 0 and 1, the population varies a bit, then shrinks to 0. But when R is within 1 and 3, the population tends to converge to a fixed value eventually. And this phenomenon could simply be explained numerically like so. We equate the next iteration of x of n plus 1, to x of n, which equals x star, which indicates a fixed point. The fixed point x star can be expanded out like so. And we find out the fixed point is either 0 or r minus 1 divided by r. Now, how can we know that it will always converge to x star, the fixed point? Why doesn't the starting value affect it? So let's check its stability using derivatives. We find that the derivative of the iterative function is this. Now we evaluate the derivative at the fixed point that we have found before, r minus 1 over r, do some expanding, and in the end we find that the derivative of the fixed point is equal to 2 minus r. We know that for a one-dimensional dynamical system like this, a fixed point is stable if the derivative of that function at the fixed point is less than 1. So for our case, the fixed point is stable when r is within 1 and 3. But after r equals 3, all bets are off. When r is greater than 3, instead of settling to an equilibrium point, the point that the function converges to starts to oscillate. First between 2 values, then 4, then 8. This is period doubling. At r equals 3.449, the period is 16. At r equals 3.544, it's 32. This cascade of doubling continues faster and faster until around r equals 3.569 and 5, and chaos ensues. This phenomenon can be represented by what's called a bifurcation diagram, which is what is on the screen right now, I hope. In this diagram, the x value is on the y-axis and the r value is on the x-axis. As you can see, as the value of r increases, it starts to diverge, splitting off, and eventually chaos. Also, here's an actual bifurcation diagram because of how painfully hard it is to draw on hand accurately due to how fast it starts to split off. Now let's investigate further on r and its effects on period doubling. So we let r of n be the value of r with period doubles to 2 to the power of n. The difference between each successive r values gets smaller, as we have discussed before on how period doubling gets faster. But if we take the limit as n approaches infinity for the ratio of successive bifurcation intervals, we find that it converges to a single constant equaling to approximately 4.669. This is what's called the Feigenbaum constant. What's interesting about this number is that it is universal. It shows up in every one-dimensional system that undergoes period doubling, not just the logistic map. Even wildly different functions like this one also exhibit this cascade, same delta, same fractal structure. So the logistic map isn't just a curiosity, it is the prototype for universal chaos. In dynamical system theory, period doubling is one of the known routes to chaos, but period doubling is special because it creates this recursive, infinitely nested structure of bifurcations. In turbulence modeling, like fluid dynamics, you'll see the same transitions: order, 2 period oscillations, 4, 8, turbulence. The same patterns appear in electronic circuits, population models, chemical reaction, lasers, even tripping faucets. Yes, really. So what is chaos exactly? Mathematically, chaos means deterministic, the system follows fixed rules, and sensitive dependence on initial values, tiny changes explode over time. And here's why that matters. People used to think if a system is unpredictable, it's because we don't understand it well enough, or maybe we're missing a few variables, maybe there's noise. But the logistic map said, nope, Even a single equation with a single parameter can behave unpredictably. Uncertainty can be intrinsic, not just from a lack of knowledge. It's said that perfect determinism does not mean perfect predictability. Even if you know the rules and initial conditions with 99.99999% accuracy, eventually, your predictions will fall apart. Weather forecasting, climate science, ecology, fluid dynamics, neuroscience, cryptography, they all had to reckon with this idea that the world might be running deterministic code, but we can't debug it perfectly. The logistic map started as a simple population model. It revealed period doubling, a path to chaos, that led to Feigenbaum's constant, universality, and dynamical system theory. And it reshaped how we understand unpredictability in deterministic systems. From one equation, one parameter, one initial value, and chaos.